Autonomous. It's a crucial part of the first tech chance that has evolved over the years. But not every team has the resources and knowledge to reinvent the wheel. That's why libraries exist. And to be more specific, motion planning libraries are synonymous with the autonomous scene. Because getting a metal box to move around on its own is a much harder task than it is believed to be. But seriously, how are these machines supposed to conquer the world if it's so complicated for them to just even park? Anyway, where was I? Oh yeah, motion planning libraries, from the classic Roadrunner vs FTC lib debate to the recent surge of popularity of pedro pathing, there's something for everyone out there. So, what does it take to be a motion planning library? Alright, let's get it straight. Minimal experience in autonomous navigation, 43 commits, and one hell of a frappe machine. Oh, and most importantly, no robot. So, our plan is simple. Create a library that the user gives as simple a series of coordinates and the robot follows them. Who's this for? This for rookie FTC teams that do not have much experience in programming the robot. It should be extensible, not require heavy knowledge of Java and the interworkings of the JVM. Documentation and loads of guides being available is an important part of the process. And it is important to not discriminate against the good old tank drive because most of teams won't use the already limited budget to guarantee their way to the all new differential swerve drive with a localization system so advanced and precise even the Thessaloniki Metro would be jealous of. No, most of them are just going to use the tried and tested dev starter base or the H base or say screw it and weld their own thing that piggybacks of the differential drive. Now, in all seriousness, it should be a robust and adaptable system able to accommodate many different drive types and localization systems. But for now, our focus is the tank drive with tank kinematics. No amount of planning equates to actual work, so let's begin. So, I created a new Android Studio project with a module that is an Android library, created a GitHub repository, made some blank classes I assumed I would need later, and called it a day. Since I didn't know where to start, I did what I already knew how to do, localization. So I copied some code from this year's FTC and it would work perfectly, right? Well, as previously mentioned, I don't have a robot to test my code on. So I started to test my library on a little simulator made by Team Beta 8397. The problem is that we can't really measure distances here. This environment makes the tank kinematics for localization non-variable since it relies heavily on the track width, the distance between the two wheels. As of editing this video, I've just discovered that the simulator has a document called Roadrunner Quick Start and inside contains the track width of the robot. So I guess that was all for nothing. Fortunately, Virtual Robot has a pretty solid IMU emulator, so we can use that to localize. Now, the problem is that the IMU interface has a very interesting, to say the least, implementation. So, the angle is represented using values from negative 180 degrees all the way up to positive 180 degrees. If it goes over any of the limits, it simply laps around to the opposite limit and counts in reverse until it reaches 0. However, robots don't always start with a heading of 0. That's why you have to allow a user to give out the starting orientation of the robot. Then we add that to the input and we're set. Not so fast. This creates an inconsistency with the negative 180 to 180 behavior, effectively messing up the entire localization system. To solve this, we just shift the angle properly using this method. After that, things went smoothly for the most part. I followed Gluten's free tutorial and made basic point following, then made the robot follow them in a series and named it sequence. Even added a tunable PID controller to enhance the precision of the following, and nothing too complicated came up. Well, until it did. See, after the robot misses a point, it decides to oscillate in this weird sine-like pattern. My instinct was to create a separate controller that detects when the robot is stuck and gives it a small nudge in order to get out of the path to the nearest black hole. It didn't work, so After some extensive research, I realized that the oscillation happened due to the angle being over 2 pi or 360 degrees. Apparently, this confused the controller and made it form this weird pattern. So, just adapt the angle and it is simple as that. Now, the library is half complete. I wonder what is the other half. Pure pursuit, or circle line intersection, is an algorithm that helps the robot navigate through a predetermined path. This is achieved by drawing a circle with center point the robot. Then it calculates the points of the path intersecting with the circle. Keep in mind by path, we essentially mean a series of points connected by lines in a sequential manner. So what we really do is checking if a line intersects with our circle. After reading the paper introducing this algorithm, I felt stuck as I couldn't figure out a way to translate this concept into code. So I looked at some implementations, but that proved toothless as I couldn't really get them to work on my codebase. But the solution was in front of me all along. See, the programmer from Gluten-Free had made a video showcasing the math behind the algorithm and explaining how it could be implemented. Great, I fitted them into the codebase, wrote some code to handle some unaccounted cases, and path following was finally working. We had one whole project documentation away from pushing this to production. Actually, maybe not. 11 commits later, you have no excuse. Fine. Right, what does it take to publish it? Apparently a Git repository and loads of headaches. First I wanted it to be on Maven Central, but after an embarrassing amount of research, it doesn't fit our use case. Then I discovered Jetpack. It claims that only with a small change in the build system file, and by creating a release on the project's public GitHub repository, anyone can download your Java library through their preferred Java build system. However, if it were that simple, I wouldn't make such a big deal about it. Yeah, reality can sometimes be disappointing. How about I take a different approach to explaining this one? The whole project had 43 Git commits, 12 of which were for actual functionality of the library. 11 of those were for documentation, and the remaining 20 were me just trying to get Jetpack to pack my library. No, seriously, it was painful. Build after build would fail. Oh, it built successfully. Too bad the executable wasn't included, so it was pretty much useless. To give some perspective, for every build I would assign a letter of the alphabet. We begin from letter A and we went all the way up to letter L. Despite its insanity, we managed to publish it. Woo! And now anyone can use it. Or, I don't know, maybe contribute to it. I'm keeping out an eye for pull requests, so if you're into this kind of stuff, you're welcome to join in. I'm planning to support this library for as long as I can. I have many plans to expand this, so keep an eye for updates and new guides. Until then, καλή συνέχεια.